good?
Mm-hmm.
Good?
Mm-hmm.
So, today I'm going to talk about homework.
That was hers that I gave you.
Oh!
This is it.
Did you give him yours? That is really impressive.
Yes.
She must have completed it.
This is your lecture notes in a hard copy for
I
it.
see.
One-sided. Say it's only things.
Holy wow, what the?
Yeah.
Making an argument for printing 2 to a page, I guess.
I used to think that it would be a good idea to print out.
It doesn't cost you any less though. They still charge you the same amount even if you print it double-sided. It writes a lot less.
Yeah, that makes me
Probably.
wonder why you should do it
It
double-sided.
doesn't sound right. But anyway.
Toner's expensive.
All right, so
I actually am trying to justify it something.
structure of subspaces. I've, at this point, told you a few things about isomorphisms, told you about quotient spaces. Unfortunately, many of these things have been released straight to video. You may or may not have seen them. We will talk more about those things as we go on here. But today I want to talk about the structure of subspaces. In particular, I'm going to start with an example, actually a definition. So, and I think you've even had this in homework somewhere. But if we have vector spaces, let's say V and W, and let's say over the reals, since we don't know any better, then that's not an essential feature though, right? Then V cross W, the Cartesian product of V and W. So this is defined in terms of set theory. It's a well-known thing. We take top pairs, things in V with things in W, right? This is something that we know from set theory we can do. But it's not just that. I mean, it's a set, but it's a set where we can define an addition and a scalar multiplication. So this pairs V comma W such that V is in big V and W is in big W. Okay, so this is a vector space where the 0 in V cross W is equal to actually 0 comma 0. Well, to be more specific, it's the 0 in V paired with the 0 in W. That's the 0 vector in there, all right? And how do you add things and how do you scalar multiply things? So suppose I have V1, W1, and I want to add it to V2, W2. How do we define the addition in the cross product of V and W? Cartesian product, I should say. And how about scalar? Yeah, scalar multiple, how do we do that one? So V1 plus, you just add component-wise, right? Oops, V1 plus W1, V2 plus W2. And here you said what?
CV, CW.
CV, CW, all right. Right. Now, so this is in fact a new vector space. So if I have these 2 vector spaces, V and W, I can create yet another vector space, V cross W, which is a new vector space distinct from the first 2 that I'm given, right? Yeah.
Why is it V1 plus W1 and not V1 plus V2, comma?
Oh, because I'm an idiot.
Oh, okay. I was
Yeah.
scared.
No. Yeah. W1 plus W2, yeah. Sorry.
Not an idiot.
When it comes to this end. So, what I wrote was stupid. So, I guess they can judge me by my actions, not your impression. All right, now, so anyway, you can prove that this is a vector space. It satisfies the axioms, right? Okay, I'm not going to do that. Then you can ask questions like, what's the dimension, right? What's the dimension of V cross W? Because your little theorem. What's that?
It's 2.
2? Well, because
Both of them are over R, like just like over like a 1 dimension, so they would go be 2.
if it was R cross R, I would agree. But the question is, what's the dimension of V and what's the dimension of W? So suppose that beta, so V is equal to say V1, V2, Vn. And suppose the betas of W, W1, W2, for the Wm. So suppose beta b is a basis for b. Suppose beta w is a basis for w. All right? Is this in framing?
Mhm.
Then the following set, beta, which is formed from two things. So one thing we do is we take v sub I, comma 0, all right, such that I is equal to 1 to n. Or the other thing we put in here is 0, comma wj, where j is equal to 1 to m. So my claim is that beta is a basis for v cross w. All right, so what does it take for, let's prove that. What does it take for beta to be a basis? We need to show what?
Linear independence.
Yeah, linearly independent, and the span of beta is equal to
Vector space.
yeah, v cross w in this case, right? I'm going to start with the spanning. All right. Are you with me?
Mhm.
So let's see. Let x be an element of v cross w. Then what? X is equal to what?
Or V,
I mean, what was the definition of v cross w? It's pairs of things, right?
Yeah,
So,
so
now what's the deal with v and w? Where v is what? V is in v, right? And w is in w. So what does that tell you about x? Well, we can write this, right? This is the same as v comma 0 plus 0 comma w, right?
That's not sense.
By the definition of the vector addition, I can break it up like that. What is v and w are both vectors in v and w, right? Those are, if beta v is a basis for v and beta w is a basis for w, what's that mean? That means that these are linearly independent spanning sets for v and w respective, right? And in particular, that means that I can build the v from the basis for v, and I can build the w from the basis for w, right? So I can write this sum, say I equals 1 to n, for some constants, let's call them c, vi. And then over here, 0 sum, let's say j equals 1 to m. I need some other letter, let's say b sub j, w sub j, like that. And then, by definition of the vector space structure here, I can pull out the finite sums and I can pull out the scalars, and look what I got. But what are these things that I'm about to underline in red? I mean, see this? See this? Those are precisely the elements of the basis beta. So this shows that an arbitrary x in the cross product is in fact in the span of beta. So therefore, beta is a spanning set. Is that a question? Yeah.
Is that an element of the span of beta, or is that what the span of beta is?
It's an element. The span of beta is a set. That's a vector. Now, how about linear independence of beta?
Well, isn't that a linear combination of B0 and 0 W, or C B0? Oh, C. Okay.
Yeah.
If you don't say it better.
would you use the thing, the proposition that says like the constants times the elements of beta equal, they have to be all like zero, like all zero, or like C1 plus V1, V1 plus C2 equals zero?
That's what I'm trying to say, but it's like, it's like,
Oh, so you guys are saying I should set a linear combination of things at the basis equal to 0?
Yes.
Try to show the coefficients. I agree. So essentially, you know, what's a linear combination of things at the basis of beta? It's this thing right here, right?
Yeah.
So, you know, I can say, okay, so, I mean, basically just take the formula above and set it equal to 0. That's the condition that I need to investigate, right? So let me just call this thing star. So set star equals 0, and notice that star, if you just manipulate back, what do we get to? Right, I can put V back in its place, and I can put W back in its place, and then I have that is equal to 0, right? But what 0 is that? You know, that's not just any old 0. That's 0 in the cross product, right? That's 0 in the, I keep saying cross product. I really should say Cartesian product. 0 in the Cartesian product, you know.
So this is still like a kind of Cartesian like system, even though it's not our square.
Well, I mean, we call it Cartesian product in honor of Descartes, who started this way of thinking about it. So,
When you say cross product, you're not talking about thinking calculus.
no,
Okay.
that was why I was saying I shouldn't say cross product. So Cartesian product. So this is 0 V, 0, comma 0 W, right? I mean, that's what that 0 is. It's in the Cartesian product of V and W. And you know what makes the Cartesian product of two sets what it is that you get pairs, right? You're creating pairs from the two sets you're given. But one of the things about this construction is that when you have two pairs are equal, that's only true if both the first component is equal and the second component is equal, right? So when I have a pair, something comma something equals something comma something, by the very construction of Cartesian product, I get to equate the first slot and the second slot, right? So this has to be equal to that, right? And this must be equal to that by the very construction of V cross W. So therefore what? Sum I equals 1 to n, Ci Vi equals to 0 sub V, and sum j equals 1 to m, Vj Wj is equal to 0 sub W. But what can I say then?
The only way that happens is if C of I, B sub j equals 0.
Why?
Because beta V and beta W are linearly independent.
Yes. Why are they linearly independent?
Because they're bases.
Right, because we assume that they're bases, so that means that they're linearly independent. So to prove the spanning, we need to use the assumption that they were spanning sets. Now to prove that they're linearly independent, it's come up that I need to use linear independence of beta V and beta W. Yeah.
But you also said because they're not empty.
No, I mean, things can be not empty and be linearly dependent. I mean, I need linear independence of this set and that set, right? So, which implies C1 equals equals C n equals 0 and B1 equals B m equals 0 by linear independence of beta V and beta W respective. Over done. Now there's some silver lining in this argument. Like, what do we get to say about then? What's the dimension of the Cartesian product of V and W as it relates to V and W?
Would it be equal to the dimension of V beta, the V and beta plus beta W?
I don't know what the dimension of beta D would mean. I can talk about dimension for a vector space. So by the same token, a subspace, after all, a subspace is just a vector space, right?
Would it be the dimension of V plus the dimension of W?
I think so, right? So, follows by counting. that the dimension of V cross W is equal to dimension of V plus the dimension of W. So what you were saying earlier, Christian, was on the right track, but you were assuming that the dimension of V and the dimension of W were one.
Well, you define them as one over R.
But over the reals doesn't need one dimensional.
Oh,
It just needs
it would
the
be
scalars.
R1.
The
Never mind.
scalars are from R, yeah.
My bad, I just assumed they were one-dimensional.
But it's important to understand that language doesn't mean one dimensional.
Yeah.
Because that would hurt you.
Yeah, I'm realizing that now.
Okay, well, hey, the test hasn't happened yet, so.
Notation is just a nightmare in this course. It's hard to do the actual work.
Notation is the course. Saying that I understand the course, but I don't understand notation is sort of the, trying to think, it's like what people always tell you. Oh, I don't know, I'm too sick to think of it. All right, so.
You've seen Bottom Naruto, but you never watched it.
What's that? Oh, you like Naruto, you just never watched it?
I don't know.
I'm not trying to say you're a poser. Okay, so there's an interesting theorem here. This theorem provides us the backdrop with which we're going to define something called the internal direct sum of the vector space. So we're getting there. Let me state the theorem and try to prove it a little quicker than what I just did. Suppose, I'll probably skip some of the proof here. Suppose A and B are subspaces of B, and let eta be a mapping from the Cartesian product of A and B to B, and let it be defined by eta of A comma B is equal to A plus B. Then, 1, eta is linear. That's just by the nature of its definition. That's not up for grabs. And I'm not going to go through the proof of that. I mean, you guys, it's pretty obvious that that's linear if you look at it. Eta is injective. Now that's not for free. We need some condition about the vector spaces A and B. So what condition do you need for A and B to for eta to be injective? We can test the injectivity of the map by looking at the kernel, right? If it's linear. So you ask yourself the question, what does this function eta send to 0? How can I have 0 here? How can you have 0 from adding A and B together?
If
A and B can be 0.
Or
Yeah, if A and B are both
they're
0.
additive.
What's that?
The opposite.
Added.
Yeah, the additive opposites, right? So in other words, you're saying if A is an A and minus B is in what? If minus A is in B, right? So if A is in A and minus A is in B, then that would be in the kernel, right? If you start thinking about it, if there's any overlap between these two subspaces, right, then you'll have both the point and its additive inverse in both copies. So you can always look at like eta of A comma minus A and get 0. So the only way we can have that not happen, right, the only way we can have just 0 mapped to 0 is for the intersection of A and B to simply contain the 0 vector alone. That's the proof of 2. So eta is injective if and only if the intersection of A and B is equal to 0. All right. Like I was just arguing, that condition gives you that the kernel of eta is just 0. And then 3. So 2 is a condition that's about linear independence in some sense, right? Injectivity of the map is tied to linear independence. How about surjectivity?
If the range is equal to, like the Quaternions.
That is what surjective means, yes. But what do we need about and this particular math eta? Like, let me start looking at 3. So I have the proof of all of these written out in the notes. I'm just going to write something about 3 here, okay? So to prove it's surjective, what will we need? Let V be an element of D, right? Now, you know that A is a subspace of V, and D is a subspace of V. That's given, right? So certainly if V is equal to A plus B, where A is in A, and then little b is in big B, then you can see that eta of A comma B is equal to A plus B is equal to B, right? So if I could take any vector in V, right, and I can write it as a sum of two things, one from A and one from B, then I can always look at eta of A comma B and map to that B. So that this, if I could, you know, catch this check here, right, if I could actually meet this criteria, that would be enough to show it's surjective, right? So how would that be?
If A equals B minus B and B equals B minus A?
Maybe. I'm not sure about that. I've written it this way. I won't rule that out, Michael. But I wrote it in this somewhat greedy fashion. If the span of A union B is just equal to B, which is, I mean, I think you can replace that with a more minimal condition if you have a basis. If you have a basis for A and a basis for B, if the span of the union of their bases gives you the whole vector space, then that's another condition. I've just stated in terms of the subspaces themselves, which is pretty greedy. But if that condition is met, right, then certainly the thing I've done in red is allowed, because the span of the union of things in A and things in B gets everything, right? So, yeah.
But what you said before that was that you wrote the span of the basis A union with the basis B.
I have no basis in here. No basis. I was talking about that. That was we're not on a basis anymore at the moment. Sorry. So anyway, if A is surjective, if the now really there's a better way to write this. I would typically not think about this past this point in the course, guys. What I would typically replace this condition with is the much more elegant way of saying if the sum of A and B is equal to B. Now, what's the sum of two subspaces? How do you define that? What should that mean if I say A plus B? Very simple. It's just this. It's x plus y, such that x is an A and y is an B. That's all it is. You can prove that that's a subspace. Just like you can prove that the intersection of two subspaces is a subspace. Although not if you took linear algebra from me in the fall of 13.
Did they miss that?
That's what Andrew did.
Who's that? It redefined the grade distribution I could consider for the class. Excuse me. All right, so that's a theorem, which gives rise to the following definition. So here's the definition. If A and B are subspaces of V, and eta is defined as we just defined it, eta is mapping from A cross B to B, comma b is equal to a plus b. If this is an isomorphism, what's an isomorphism?
This is an invertible linear transformation.
It's an invertible linear
Right, this
transformation.
linear transformation has an inverse that maps backwards too.
Such that the dimension of A cross B equals the dimension of B.
Some subset of things I just heard are correct. I'm not sure. As much I can say, it has to be linear, it has to be injective, and it has to be surjective, right? Injective and surjective. In other words, a isomorphism is a linear bijection. We had a theorem actually that said that if you have that the function is invertible and if it's linear, it automatically followed that the inverse was also linear, which is kind of cool because in other math, you actually have to check the criteria for the inverse. For example, in topology, to have something as a homeomorphism, you have to show that the function's a bijection that's continuous with continuous inverse. It turns out that continuity of the forward map does not imply continuity of the backwards map. But here it is. If I have a bijection that's linear, it automatically follows that the inverse of the bijection is also linear, which saves us some work if you think about it. Okay, anyway, so if this eta is an isomorphism, then we say V is said to be the direct sum, internal direct sum. I write A is equal to A plus circle B. AB is equal to A plus circle B is the internal direct sum. Internal direct sum of A and B. All right. Excuse me, guys. I'm so sorry. Now, let's see here. What can I say? For two vector spaces, like we're talking about, so two subspaces A and B. I should say just a word of caution as you're reading mathematics beyond this course. Some people don't use the notation the same way I'm doing it. In fact, I think there's some disagreement about this, probably based on viewpoints on pedagogy, whatever. I just chose a path. Some people would insist that A plus B is the Cartesian product of A and B, given the direct sum. The direct sum, the Cartesian product. So some people would say that this is the Cartesian product of A and B. And then, I don't know. I'm using this for internal direct sum, and the external direct sum, the Cartesian product of A and B, I'm insisting, for the sake of logical clarity, that we write as A cross B. Okay, so there shouldn't be confusion. Okay, just getting back to the point. If I have vector space, I have two subspaces. Just if you want to forget about the eta mapping, when does it suffice to say that it's the direct sum of say, A and B? Let's see here. For two subspaces, right? When there's an isomorphism, but I want to say, forget about the eta mapping for just a second. Two subspaces, right? We have A subset, A and B subspaces of B. Then B is equal to A direct sum B, excuse me, A direct sum B. This is called the direct sum, by the way.
Would you just say that the basis of the basis of B added together equally?
Well, that would be a technical criteria, but I mean, that's part of it, yeah. So B is the direct sum of A and B. It can only have what? We get two conditions. How about this? One thing is B is equal to A plus B. Right? What's the other condition I need? And what?
And the intersection is the 0 set.
Right. And the intersection of A and B is just 0. So just in terms of subspaces alone, that's the definition of internal direct sum. I mean, so in terms of like a cheesy notational justification, it's like the only thing in the middle of A and B is zero.
Plus and zero.
Okay, sorry, it's awful, yes.
No, I was just.
No, okay. All right, so let's see here. And now we got this, we can do something here. How about theorem? If B is equal to the direct sum of A and B, then V mod B is isomorphic to what? So what is the quotient, V quotient by B? What does that mean, like intuitively? What does it mean to take the quotient of something in vector space context? Intuitively speaking, what are you doing with the things in B? What are you thinking of them as being?
Getting rid of them?
Getting rid of them, yes. We're putting them all to zero, right?
What? One.
No, zero. So when we take the quotient of things, the quotient by B, that's essentially thinking of everything in B as being the zero for the new space, right? So if everything in B is like zero, what are you left with? A, right? So that's in fact the theorem.
Oh, wait, yeah, okay.
Now I'm going to give you the proof, and we're going to use the first isomorphism theorem to prove that. So to apply the first isomorphism theorem, I need a linear transformation which goes from the vector space to the other thing there. Let's see here. So I think what I can do is use this mapping T of, let's say, A plus B is equal to what? Oh, you want to use A or B? Yeah, A. Now here, I'm assuming that each V in B has A and A and B and B such that B is equal to A plus B. How do I know that? If I'm assuming it's the internal direct sum, right? That means that this A is an isomorphism, right? So what's, that means that there's just one pair which maps to B, right? So I'm using that A is an isomorphism in order to understand that there is an A and a B which give me back B. In fact, because eta is isomorphism, this choice of A and B are unique. All right. So I'm trying to tell you is my mapping is well defined. I can in fact, that is a generic point in A plus B, direct sum A, direct sum B. I can take a generic point as being A plus B where that is a unique A and a unique B and B such that I get A plus B. There's only one A plus B in the direct sum. There's no other way to get to it. Is that a linear transformation? Yes, T is a linear transformation. You can check it. It's not hard. Is what's the kernel of T? Well, first of all, what's the range of T? We'll make a couple observations. Number one, T is linear. Two, the range of T is what? A, right? What's the kernel of T?
It's B.
It's B, right? because it says, excuse me,
Right?
not really, B is 0. T of B is 0. And so I can apply the first isomorphism theorem. Hence, A direct sum B mod kernel of T is isomorphic to the range of T, right? But that is exactly, that's saying that A direct sum B mod B is isomorphic to A. So for me, as I try to understand what quotient space, the idea of a quotient space is, to me, most of my examples that I really understand nicely, they're very much tied to some particular direct sum decomposition of a space. This is a direct sum decomposition of B in terms of A and B. Excuse me, guys. Goodness gracious. Now, perhaps you'd like some examples. Let me give you some examples. Yeah, okay.
One course is being class teacher.
What's that? Oh yeah, this one's the evil one.
It's a bad eraser.
Yeah, it's I'm not sure it can really be called an eraser.
Smudger.
It's a smudger, yeah. It's probably more appropriate. So some simple, no, so by the way, notation. There's a notation which makes these examples much more enjoyable. So if you want to talk about the span of say V, there's a better notation for this. If we're looking at the real span of V, you should just say V times R, because that's what it is. Or you could say, I don't care. I guess you could say RV, but I almost always use this, all right?
That would make a lot easier to understand spans.
So for example,
Maybe I'm crazy.
R2, all right, what is R2? R2 is, actually you could think of it as this, it's E1 times R plus E2 times R. Now, can I put a circle around that plus? Is this in fact a direct sum decomposition? Geometrically, here's X, here's X2, here's X1 if I'm using that notation. You pick any vector here, there is a unique one of these and one of these that gets there, right? So, I mean, this is X1, E1, right? Let me do the other. E1 times X1, I mean, E2 times, I mean, whatever. The point is that this is an element of E1R, and this is an element of E2R. And there is only one way. There is only one choice of the horizontal and the vertical displacements to get to that given point in the plane, right? That's that uniqueness I was talking about over there in the purple net proof. So yeah, I can put a circle around this. This is the direct sum of the x and the y axes. Another example. Complex numbers. What do complex numbers look like?
Something equals BI.
Right? A and B are real numbers, right? So I could rewrite that, in fact, as 1 times the reals plus I times the reals.
There's going to be like D or something. Why is it 1 instead of a variable?
Is 1 a complex number?
Well, it's not, but I was wondering why.
Yes, it's because the reals are a subset.
No. So I wouldn't even usually bother writing the 1 in front of R. I would just write this as R, in fact, direct sum IR. Now, there is an isomorphism to this in R2, right? Like I can say that this is isomorphic to R2, and the mapping, the isomorphism, is this. It's A plus BI is equal to A comma B. That's absolutely true. And in fact, that's more than just an isomorphism in the sense of linear algebra. I can actually build a multiplication on R2, which mimics complex multiplication. And in so doing, construct a model of the complex numbers using two-component vectors if I want to. It's true. I'll talk more about that Wednesday. We can stop talking about that now. So anyway, yeah. Complex numbers are the direct sum of real numbers and pure imaginary numbers, right? IR is the pure imaginary numbers. Make sense? What is it?
I'm wondering what that symbol is.
This?
Yes.
Pitchfork. Psi.
Oh, there's the red one.
Get fun out of it. All right. Another example would be the Quaternions. H. These are the direct sum of the reals, I times the reals, direct sum J times the reals, direct sum K times the reals. All right, and there's a 1 here. Now, this is notation. These 1, I, J, and K, right, these guys, these are, this is a linearly independent set. All right, over the reals. Now, there are different ways you could construct those things in terms of matrices or whatever, but formally speaking, a quaternion is built from, typical quaternion looks something like, you know, W is equal to T plus Xi plus Yj plus Zk. So every quaternion looks like, you know, like there's a real part of the quaternion plus like the vector part, let's say. You might recognize the IJK, right? Like from Calc 3. Or physics, perhaps. Remember IJK unit vectors? These actually behave like that. You can define a multiplication here. You can recover dot products and cross products. You can say more about that. That's kind of beside the point. It's just another nice example of quaternions are a direct sum of these four one-dimensional subspaces. Let's see here. Let me move on. So, excuse me. Oh, great. So I got sick over there. You may have noticed. I played with cousins. They brought an out-of-state virus into my house. Let's see here. What about 3 spaces? I mean, there are other things you could do, guys, before I go on. How about R3? You could also write R3 as something like this. Do something like, it's okay, it's E1R, direct sum E2R, direct sum E3R, that's true. But you could also look at this, like these two things collectively as something. What is this?
Is it not R2?
It's, well, it is R2. It's R2 sitting inside R3, though. Let's be careful, right? This is the XY plane embedded in R3, right?
And it's just this is 0 line.
Well, there is a slightly different. I mean, so what I mean that is the XY plane, I would say, is just R2, right? So if I want to talk about an isomorphism, I could say phi of x comma y, right? To embed that in R3, the mapping is just psi of xy is x comma y comma tack is 0 on it, right? Not a big deal. That's an injection, it's an isomorphism. Technically, there is a difference between having 2-component vectors, right, and having 3-component vectors. So, but it is common that we identify the embedded version of the xy plane as the xy plane, right? It's not a, well, it doesn't confuse students too much, right? As long as you don't talk about the fact that you're doing it. If you admit that you're doing it, then they're confused. So just don't admit it. As a teacher, hide these things. Don't tell people the truth. Okay, so what I'm trying to say is actually R3 is the direct sum of the xy plane and the z-axis, right? Or you could say that R3 is the direct sum of the yz plane and the x-axis. You have you have lots of choices, in fact, right? Now, what if we talk about direct sums of three things? Let's talk about that a little bit today, and then that'll be where I stop. What if you wanted to, let's say, V is the direct sum of A, B, and C? What would you like? I mean, what should the definition be? The definition for three subspaces is just like let's add just another subspace up there. Yes, Landon?
Like in photography where you had, there are two different ways of like getting to a point, like, or adding things, I guess. Like you could do like the x and y, and then I guess like the explicit and implicit thing.
I'm not sure. I have to talk to you for a while.
Okay.
Search the. There's typically something to what you're saying, Landon, but it takes me some time to dig down into it. So what should this mean, the direct sum of A, B, and C? I'm saying this should be the definition, basically, is that this mapping, A of A, B, C, is equal to the sum of A plus B plus C. This being an isomorphism should be the definition. That would mean that everything in the direct sum of A, B, and C, you can uniquely find, if you give me B, an element of A direct sum B, direct sum C, it ought to be the case that there exists a unique A and A, B and B, and C such that
They all add up to B.
exactly. Right? So I think there's a temptation to think that it suffices to know what, I mean, you might think that this is a sufficient condition. B is equal to what? Surely you need A plus B plus C. I mean, we are all on the same page with that, right? Surely it must be that the sum of the vectors subspaces gives you a little space. That's got to be, right?
It's supposed to be isomorphic. Or rather, it has to be, sorry.
It's okay. And then I was tempted, and in fact, I think a lot of people are, to say, well, it should be enough to know that like A intersect B is 0, right? Well, I better also have that B intersect C is 0, right? What else do I need? A intersect C is 0, right? Like, you'd think that that would be enough, but you're wrong. Let me show you why. There's an error in the notes. Not enough. Not enough. For example, if you look at, you can say R2 is the direct sum of, let's say, 1, 1, R. Well, not direct sum. You can say R2 is 1, 1, R plus 0, 1, R plus 1 minus 1, R. In my notes, I put 1, 1 here. I think it's more interesting if I put 1 minus 1 here. Okay, so if you think of this as being A, think of this as being the B, think of this as being the C, you can see that the intersection of any pair of those is 0, right? Because like these are not collinear, and yet certainly it's not. I mean, it's not going to be a direct sum decomposition. Like if I pick, let's just pick a vector. Gee, I don't know. How about? Goodness gracious, I'm trying to think of one here. How about 2, 2? Can you think of different ways to write that? I mean, obviously it's 2 times 1, 1, right? What else is it?
2, 0 plus 0, 2.
Say again?
2, 0 plus 0, 2.
2, 0
2
plus.
comma 0 plus
I need to build it from things in here
Okay.
though. So I'm looking for a multiple of this one, that one, and this one, other than this, which gives me back 2, 2.
So you could do
2A
like
plus 2B? No.
2 times 1 minus 1.
2 times 1 minus 1.
plus 4 times 0, 1.
4 times 0, 1, yeah, for example. So that alone shows you that the eta mapping is not an isomorphism. It's part of the eta being injective means that there's a unique representation between the sum of things in each vector space and the V. That's not the case, so it's not enough. There's something more subtle that's needed as a condition. And that is given on page 184 of my notes. I'm just going to say the words here today. There's 4 conditions to say that V is a direct sum of, say, K subspaces. First, one of the conditions is that you've got the K subspaces, all right? And the union of bases from each subspace forms the basis for the whole space. That gives you that the eta is an isomorphism. The other thing you can do is to say that any finite set, all right, where you're taking 1 from each of the subspaces, all of them non-zero, is linearly independent. That criteria for theorem 7.711 becomes the generalization of this intersection, the trivial intersection condition. So the trivial intersection condition does not generalize naturally. You got to look at part 4 of theorem 7.7.11, and maybe I'll talk more about that next time, but I know more time, so I'm shut up.
Couldn't you add A intersect B intersect C? And would that be the right condition?
The intersection of 3 of them is 0.
Yeah.
I don't know how to say it exactly in terms of intersections, but some spaces I don't know if I have.